Really? Yeah. It's not like two. It's not like I got 5 at the same time as a regular.
All right, let's take a look at page 193. We're going to start our last section of the unit today, and we'll wrap it up tomorrow, just in time for your partner quiz on Wednesday. So today and tomorrow we're going to take a look at derivatives of inverse functions, and I know we spent quite a bit of time last year talking about inverses, and we'll revisit those relationships and properties today to help us with derivatives. But these are, let's see, in my opinion, not terribly difficult. We're going to have to kind of wrap our mind around it, though. It might take us some time to get used to it. But in all honesty, these do not show up very often on the AP exam. But if they do, it's like one question or two. So it's something that would be nice to go over, but it's not as heavily important, if you will, than some of the other concepts that we've dealt with so far this year. So can we dig deep from last year and think about what are some things that we remember about inverses? What are some properties? What does an inverse mean? Good question?
You switch the x's and the y.
Okay, so an inverse is numerically defined to be the function whose x values and y values are switched. I say that's pretty much a solid definition of an inverse. So we're going to just briefly take a look at a graphical example, like how we can switch x and y points or ordered pairs on a graph. And then an analytical approach would be some type of relationship between the equations. Okay, we're not going to do the bottom half. That's if we really truly needed a review of inverses, which I think we're good. But we'll revisit this if we have to. We'll see how the derivative ones are going to go. So a graphical representation, let's say that the point on f of x was 3, -4. What would the point on the inverse of f be if we used Christian's definition? There we go. All right, so we're just switching the x's and the y's. Okay, we're not making anything opposite. We're not making anything negative. We're just switching. Okay, sometimes students get confused with switching or inverse because inverse sometimes you think opposite, meaning switch the sign, but that's not the case. Okay, we're just switching the values. Now, there is some relationship between the equations. For instance, if you were to take the inverse equation and plug it into the original, do you know what you'd get out? Yeah? X. Okay, that was actually one of your questions on the pass-fail test. Okay, we can take our time to look at an example. Can someone give me a really simple equation? Maybe a line. X plus 1. Okay, let's go ahead and find the inverse. So if we switch the variables and we solve for y, the inverse would be x minus 1. Okay, now truly this notation doesn't really matter. You can put the inverse into the original or the original into the inverse. It doesn't matter which way you operate it. Okay, we should get x back. So let's say we took this x minus 1 and plugged it into the x in the original. Okay, we'd have x minus 1 plus 1. The ones would cancel and we're just left with x. So this is an algebraic relationship between inverse equations. So we have point relationships, we have algebraic relationships. We're going to explore those two concepts today, okay, related to inverses. Does that ring a bell for us, switching x's and y's? Okay, we're going to go ahead and flip to the back. So if we know that this relationship is true, if we were to plug the inverse into the original and we should get x, we could probably find the derivative of that equation, maybe using some shortcut rule. So can you think about a shortcut that we could probably use? If these were like really big parentheses instead of brackets, I mean, they might mean the same thing. Yeah? We got a chain. We have an inside and an outside piece. Okay? So let's go ahead and try our chain rule. We would need the derivative of the outside, which would be f prime. We'll keep the inside, which represents the inverse. And then we have to finish the chain rule by multiplying by the derivative of the inside. So somehow we're going to have to represent the derivative of an inverse. So we can't really put the prime mark after the f, because notice how the -1 is already there. Okay, we're not going to put two symbols next to each other. We're going to represent the derivative of an inverse kind of like that. We'll have the inverse prime. So maybe we'll write that at the bottom. Derivative of inverse. Okay. So we have the outside, or the derivative of the outside, keep the inside, times the derivative of the inside. And then what about the derivative of the other side of the equal sign? The derivative of x is 1. Okay? So in this section, we actually created a formula or a rule to help us find the derivative of an inverse function. If we wanted to get this portion all by itself, notice how everything's being multiplied together, we'd have to divide this piece to the other side. So we can say that the derivative of an inverse equals 1 over f prime of the inverse. I know it just went over our head. It's going to make more sense when we go over some examples. Okay. So this is a basic formula we can use. I know some of us are procedural and would prefer like certain things to look for. So on the right hand side over here, I'm going to go through some criteria or steps that we can use to our advantage. One thing that we're going to do first is we're going to find a corresponding x value. Okay, and you'll see why in a second. So we're going to find the corresponding x value. Notice how we have to find the derivative of the original function at some point. So we're going to say we'll find f prime of this value. And once we find the derivative of this corresponding point, we just need to do 1 over that. So we'll just reciprocate it. All right, so some of you might prefer a formula, some of you might prefer a procedure or some steps. We'll go over both ways. Okay. So the notation can get tricky because we have all these different symbols or function notations and primes being thrown around. We're going to just do a simple one first, and then we'll get into kind of a table example. Suppose that the original function is 3x plus 2, something really simple, and the derivative specifically at -2 is 3. Can we think about what the derivative at any other point would be, by the way? 3, why? Everywhere. It's always up 3 over 1, up 3 over 1. So it actually doesn't matter what point you put here, the slope would still be 3. So somehow with this information, we have the value of the what's the derivative value, there's that little prime there, the derivative value of the inverse at -4. Now what would probably be simple is we could figure out the inverse equation, right? We could switch the variables and solve for y. We might not always have that available to us, but maybe we'll check it out anyway. If we were to switch the variables and solve for y, we could subtract the 2 and then divide the 3. So 1/3 x minus 2/3. All right, there's our inverse. What if we took the derivative of that? The derivative of the inverse would be 1/3, okay? And if we were to plug in -4 into this derivative, what would we get? It's still 1/3, right? It's still a line. There's no x for you to actually plug it into, so this is going to be the answer for any point. So by looking at the equation, we can figure out what this the derivative of the inverse would be. But we might not always have an equation available to us, and even if we do, finding it this way by switching the x's and the y's might not be possible. For instance, you might not be able to get the y variable all by itself. So this is when we have the formula or the steps to kind of help us figure it out this alternative way. So what can be tricky is notice how this -4 is an x value for the inverse. What would that mean this -4 is for the original? It's a y value. Okay, so we'll say x value in inverse means y value for f of x. So if we know the y value for f of x, we can figure out the corresponding x value for f of x. So if this is an x value for the inverse, we should be able to figure out the x value in the original. So we can take this -4 and plug it in for the y spot. And what happens if we solve for x? Can we find the corresponding point? Subtract the 2, divide the 3, we'll get -2. Okay, so this is your corresponding x value. Even though they're asking you for the derivative at -4, you can actually use this x value to help you figure it out. So if this is the corresponding x value, we want to find the derivative of the original function at this spot. So what did we say the derivative of -2 would be? Do we know that information? 3, right? Or just the slope of this line. All right, so we found the corresponding x value, we found the derivative of the original at that spot, and last but not least, we just have to reciprocate the answer. So if we were to flip 3, we'd get 1/3. Okay, and notice how that's the same thing we got if we actually worked it out by hand. So this is all well and good if you have an easy equation, but you might not have that ability or information available to you. That's when kind of this step or this formula process will help us figure out the slope of the inverse function at some random point, whatever point we want to pick. Okay, so I'm hoping this is going to make a little bit more sense when we check out a table, okay, because we don't have an actual equation to work with. So in this table, we have f, g, and derivative information or values. They do this a lot on the AP test, just throw a lot of random numbers at you to kind of confuse you, but it's going to be a lot of table reading that we're going to have to get accustomed with. So they want us to find the derivative of the inverse specifically at 3. We don't have an equation to help us out like we did previously, so this is when those steps or properties can help us out. So let's see if we can find the corresponding x value first. If this 3 is an x value in the inverse, notice how we don't have any inverse information, what does this 3 also represent? A y in what? The original. Okay, so notice how this is the f column, the original function column. If we can find the y value of 3, notice how the corresponding x value would be 1. Okay, that's your corresponding point. So I know they're asking you for the derivative at 3, but you can use this x value of 1 to help you out with that. And notice how they wanted to confuse you even more, because didn't they give you an x value of 3 in the table? That can be tricky. Okay, so here's our corresponding x value. We want to find the derivative of the original at that spot. So do we know what f prime of 1 is? 2. Okay, and once we have that value, since our formula is 1 over the derivative, we're just going to reciprocate that answer. So if we reciprocate 2, we'll get 1/2. Okay, so there's the derivative of the inverse specifically at 3. I don't want you to confuse this with normal. You know how for the normal slope you do the reciprocal as well, but you do the opposite because they're perpendicular? Okay, this is just a reciprocal. This does not become negative 1/2. Okay, you're just flipping a derivative value. All right, let's try another one. So we want the derivative of the inverse of g at -2. Can we find the corresponding x location? If this is a -2 x value in the inverse, good, then it's a y value in the original. So we happen to have the same corresponding point. Now that we have that point, we're going to find the derivative of the original function at that spot. So g prime of 1 is also 1. Okay? And then if we reciprocate 1, also 1. Look how confusing that is. Okay? That one was a little tough. So not only is the slope 1 on the original graph, but it looks like it's also 1 on the inverse graph. Even though we don't have the graph available to us, okay, we can figure out that information. All right? Let's keep this train rolling. More table examples, and I think it happens to be the same table. So this is a pretty good example of a free response type question where they give you a table or some information at the top and they're going to ask you different questions about that as the question goes on. So the functions f and g are differentiable. What does that mean? Differentiable?
Same slope each time.
Okay, so they're connected smoothly. Okay, same slope from the left and to the right. Okay, so the slope or the derivative exists. Maybe we'll do derivative. So derivative exists. What else do we know? It's continuous. Okay. Okay, differentiability implies continuity. So even though they didn't specifically state it's continuous, by using differentiable, it's implied. Okay, so you automatically know that. So we have continuous original functions, and their first derivatives are shown in the table. Answer the following questions. All right, so for the first one, find the value. I know it's a little difficult, but there's the prime on the outside. So find the derivative of the inverse at 1, and then find the equation of the tangent line for the inverse graph at 1. Okay, we'll do one thing at a time here. Let's go ahead and try to find the derivative first. So if you want to think about your criteria or your steps, your process, if this 1 is an x value in the inverse, we got to find the corresponding x value for the original. Can we get it? 3. Okay, so here is 1 as a y value in g, which means the corresponding x value would be 3. Okay, so now that we have the corresponding point, we want to find the derivative of the original at that spot, which would be -2. And lastly, we need to reciprocate that, -1/2. All right, so this is the derivative of the inverse specifically at 1. Okay, but now they want us to find the equation of the tangent line to the inverse graph. Okay, a little tricky here because normally they ask us about an original function. So we still need to find a point and a slope, but that information has to come from the inverse because that's the graph that we're drawing the tangent line on. So we need g inverse at the x value of 1 and the derivative of g inverse at 1. Okay, point and slope. Do we know one of those already?
Yes.
Which one?
The slope.
The slope. Okay, we had -1/2. Do we know the point on the inverse graph? That's 3. That's actually what we found in the first step, that corresponding point. So if this is an x value in the inverse, it's a y value in the original, which means your output would be 3. All right, so point and slope. By doing this process, you're actually finding both pieces of information, okay, the point value and the slope value. So putting them together, we can do y minus the point equals the slope times x minus 1. Looking good. All right, let's try the next one. Estimate the value, oh good, no inverse. Estimate the value of the derivative of -1 for the g-graph. Based on this value, what conclusion can be reached about the g-graph at that spot? How do you want to estimate, approximate a derivative value? G prime of -1 is roughly pick 2 points. Okay, one before, one after. So the slope of a secant line should be really close to the slope of the tangent line, aka derivative. So this is roughly the slope on g of x between x equals -2 and 0. Okay, so we'll do the slope between 2 points on the g-graph. So we're going to need change in y's over change in x's, y2 minus y1 over the x's. So maybe we'll do -3 minus 2, okay, change in the y's, over 0 minus -2, so that'll change to a plus. And we'll get -5 over 2. Okay? So that's roughly the slope at -1 on the g-graph. Based on this value, now that we found it, what conclusion can we reach about the g-graph? What's this negative derivative symbolizing? A negative slope. And if you have a negative slope, how's your graph acting? Decreasing. All right. G of x is decreasing at x equals -1 because g prime is negative. All right. That one's kind of a review question for us. I'm interested in thinking, can we do the same analysis for a very similar type problem? If you read the next one, it's basically the same. Estimate the value of a derivative based on your conclusion. What do you say about the graph? What's the difference? It's the second derivative. Estimate the value of the second derivative. So how might we estimate that slope? What do you think, Anuj?
Use points for g prime between 0 and -2.
Okay, so if the first derivative is the slope of the g-graph, then the second derivative is the slope of the g prime graph. Okay, the first derivative, it's the slope of a slope. Okay, 2 derivatives, 2 slopes. So slope of g prime between x equals -2 and 0. So based on the table, we now are going to use 2 and 3, okay, from the g prime column. So we'll have the change in the y's over the change in the same x's. Looks like we'll get -1 over 2. What does this tell us about the graph of the first derivative? G prime of x is decreasing at x equals -1 because
slope is negative.
the slope is negative. Or in this case, g double prime. Yep, the slope is negative. Perfect. So we have the same graphical relationships or characteristics between higher order derivatives as we do between the first derivative and the original. Okay? And we're going to explore that concept on the next page. Okay? So before we tackle an actual AP free response type question, let's explore these higher order derivatives a little bit further. So we know up to this point that whenever we have a y equals equation or an f of x equation, this is just representing kind of an original function. And in terms of like finding a slope of a tangent line per se, this is going to give us a point. Okay, so a point on the f of x graph. What does our first derivative represent? We know it's slope, but it's slope of what? Slope of tangent line. Okay, so slope of tangent on which graph? The original. Okay, slope of tangent on f of x. Now we can relate this back to how we were dealing with rates of change in those units, like miles per hour, feet per second, miles per gallon. So this is also representing the rate, and specifically the rate at which f of x is changing. Okay, we are already familiar with those two concepts, but now we can start talking about higher order derivatives. Notice how this would be the second derivative. So this is the slope of the tangent line on which graph? F prime of x, okay? So in terms of rates of change, this would be the rate at which f prime is changing. Okay? It's the same connection, it's the same relationship, it's just between two different functions. Instead of using the original and f prime, we're now using f prime in the second derivative. What do you think would happen if we moved on to the third? Same thing, but now this would be double prime, right? And the rate at which the second derivative changes. If we move again, the fourth derivative would be the slope of the tangent line on the third derivative, or the rate at which the third derivative changes. So we have the same connection all the way through, it just depends which two functions you're using or you're analyzing. Okay, and we're going to explore this much more in a future unit, okay, but it lends itself well right here. All right, so let's kind of use these higher order derivatives to help us with an actual AP free response type question. We're going to pick apart the terminology here. The twice differentiable function. That's a little bit new to us. What do you think that's signifying? Twice differentiable.
The second derivative.
Okay, so you can take two derivatives. What else is that signifying? Okay, so if you can take two derivatives, two functions are continuous. The original and the first derivative. Okay, so f of x and f prime of x are continuous. Okay? So if we had to, we can take two derivatives, and we already know that the original and the derivative are continuous. No holes, no jumps, no asymptotes. Let's see, for all real numbers, we also have these conditions. F of 0 equals 2, f prime of 0 is -4, and the second derivative at 0 is 3. Okay, good things for us to know. The function g is given by, it might be a little hard to read, but it's e to the ax power plus f of x. And they tell us that a is a constant. They want us to find the first derivative at 0 and the second derivative at 0 in terms of a. So we might have an a left. Okay, it might not just be a number like we're used to. You might have an a left in your answer. So let's try the first derivative because we need to have that first before we can do the second derivative. So let's think about some shortcuts. Can we find the derivative of e to a power? Remember that shortcut? What is it?
No, it's,
That's a natural log.
it's e to that, it's the same thing.
E to that power
Times the derivative of that, like, in this case, a.
times the derivative of the power. So if a is a constant, a is a number, what's the derivative of ax? Just a. Like if it was the derivative of 3x, it would just be 3. All right, so here's the derivative of the first term. We now have to add the derivative of f, which we can write as f prime. All right, now maybe we can clean this first part up here. We can move the constant of a out front as a coefficient. And I'd say that's a pretty cleaned up derivative. Let's go ahead and plug in 0, okay, because they wanted the derivative at 0. What's e to the 0 power? 1. So this would be 1 times a, which would just be a. And then we have to add f prime of a, or sorry, f prime of 0, which is -4, right, based off of the information at the top. So there's our first derivative specifically at 0. And it's in terms of a, because notice how there's an a left. Okay, that's perfectly acceptable. Let's go ahead and try to find the second derivative. So taking our cleaned up first derivative, we're going to go another round. Now, a is a constant or a coefficient, so we can keep that in our next derivative. We then have to figure out what's the derivative of e to a power. E to that power times the derivative of the power, which would just be a again. And then we have to add the derivative of the first derivative, the slope of the first derivative, which would be the second derivative. Okay, if we clean it up, we can do a times a, which would be a squared. And let's plug in 0 to get our second derivative value. So e to the 0 was 1 times a squared will just be a squared. And then we have to add the second derivative at 0. 3. Yep, based off the information at the top. All right, so there's our second derivative at 0. How do you guys think you would have fared on that part? No way?
Nope.
No?
Not really.
Does it make sense if we walk through it?
I
Yeah.
think so.
Was it the e derivative shortcut?
Oh,
Yeah, it's been a while since we've done
yeah.
that.
Yeah, it's logical.
It's logical.
I'm not saying don't do it.
It's only logical, right? Okay. Well, it makes sense. Okay. It's just going to come with practice too, guys. I mean, we're going to spend a lot more time on these free response type questions. Let's try B. The function h is given by cosine of kx times, read out loud, times f of x. K is a constant. Find the first derivative of h and write the equation of a tangent line. Okay, we can do this. So let's try to tackle the derivative. Can we think of a shortcut we're going to have to use? Product, because we're multiplying two things together.
And then chain,
Where's the chain? Yeah.
probably would be cosine.
Cosine of kx. If it's anything other than x, it's most likely a chain because you have that inside piece to take the derivative of. So product is the overall one. So we're going to start with product, and in that process, we're going to need chain. So let's do our product rule. We'll have 1 times d2, so that would be f prime, plus 2 times d1. Okay, so we're going to have to do a chain here. The derivative of the outside. So what's the derivative of cosine? negative sign. We're going to keep the inside, which is the kx, and then finish the chain by multiplying by the derivative of the inside. It's just k, because k is a constant. K is a number. All right, now, you can leave it like that. You can clean it up. It's completely up to you. Since this is a free response question, you can leave it like that. If you clean it up incorrectly, though, you might lose a point. So since it's a free response, maybe leave it the way it is just for your sake. Okay? But now that we have the derivative, we should be able to find the equation of the tangent line, because that's going to help us find the slope. Maybe we'll do that first, since we have the derivative. So let's plug in 0. Cosine of 0 is 1. And then we've got to multiply that by f prime of 0. Negative 4, based at the top. Then we got to add f of 0, which was 2, times negative sine of 0, 0, and then times k. So what's our slope? Negative 4, because the 0 on the other term is going to make it go away. All right, so there's our slope. Let's go ahead and try to find our point. So that would involve plugging in 0 into the original function, okay, the one that they gave us in the problem. So we would need cosine of 0, which is 1, times f of 0. Do we know that? 2, right? That was at the top. So it looks like our point value is 2. So putting them together, y minus the point equals the slope times x minus 0 in this case. Right? So this is kind of the expectation and a little bit of the rigor that these free response questions are going to have. Notice how it's a merger of many concepts that we've discussed so far. We've done product rule, we did chain rule, we did equation of tangent line, we had an exponential derivative to work in there, we had higher order derivatives. So these free response type questions are going to bring in many concepts into one question just to test to see how familiar you are with these. So I understand if that first one was rough, but we're definitely going to have more as the year goes on. Okay, just practice, 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 getting used to the terminology, the wording, the expectation, all that stuff. Okay, we're going to stop there for today, and we'll continue talking about inverses tomorrow.